Thank you. Sorry for the delay. Can you hear me okay? Yeah. Okay, so yes, I've talked about dark matter phenomenology beyond the WIMP paradigm. So just to start with, I won't go into much detail about the evidence for dark matter, but we have many independent evidence for dark matter from scales of galaxies up to cosmological scales. And basically, we need a matter that cannot interact with light as a normal matter to explain the stability of galaxies from embodied simulations, rotation curves of galaxies, why the stars and the gas rotate like faster than what we would expect from Newtonian physics. Also, merging galaxy clusters, we have evidence that most of the gravitating matter is not in the center of, it does not coincide with X-ray emission that we expect from normal matter and from the gas. And also from the cosmological point of view, we need a matter component that start forming structures much before the release of CMB. Otherwise, we cannot explain the structures we see in the universe today. And also, the Big Bang nucleosynthesis says that the baryonic matter explains only, accounts for only like 5% of the cosmic energy today. So we need non-baryonic matter. And also the features of the cosmic microwave background spectra are explained, the best explanation is to have a matter component also, to fit the spectra of the CMB. So basically the simplest explanation for all these pieces of evidence is to assume dark matter, a dark matter component, and likely made of particles. Sorry?
You say just a curiosity
From an
as an outsider,
yes.
complete outsider. You say the simplest, so there are others as well?
So there are alternatives to explain, for example, rotation curves of galaxies, and can explain even better than dark matter particles in some case for some galaxies. But if we want to explain, for example, the CMB, the merging cluster observations, all at once.
So the strength of this paradigm is that it can explain everything with one single concept.
Yes, in the most simple, approach.
Sorry, I have another question also as an outsider. The motivation of early universe, I never heard before. What's the motivation?
For the structure formation?
Yeah.
Because like structures, like for the baryonic matter to start forming structures, if they interact a lot with photons as normal matter would interact, the structures would form only after the release of the CMB, after the decoupling of photons. And just after that, we can have like structures like the gravitation fall. But we need like a component of matter, so it gravitates, so it forms structures as normal as matter, but it does not interact with photons. So it is not bothered by the photons, avoiding the structure formation. So dark matter would form structures much before the release of the CMB, and the baryonic matter would fall into the potential.
So interacting with photons would stop it from forming matter before the CMB? Is that what you're saying?
Yes, like they ionize and they don't allow structures to accumulate.
Okay.
Yeah, so this is like one of the most important. Of course, it doesn't need to be necessarily the dark matter that we need for other pieces of evidence, but the simplest explanation for all this puzzle is to assume a matter component that's not baryonic, and that's my next slide. So basically the evidence that we have is that we need an effective neutral component, do not interact with photons as normal matter, weakly interacting with the matter that, like the baryonic matter, because we didn't detect it yet, and also with itself, because of the merging cluster observations, for example. It needs to be non-relativistic or a matter component at structure formation, when the structure formation starts, and also cosmologically stable, because otherwise it would not be a cosmic relic in the universe. Okay, so none of the particles that we know have all these properties. So the very existence of dark matter particles points to the need for new physics. So we do need physics beyond the standard model of particle physics to explain dark matter particles. Okay, and of course we have countless models of particle physics with viable dark matter candidates, but a successful dark matter model must provide the current relic abundance that we infer from the Planck satellite observations.
Sorry, so it has to be massive? So it can't, non-relativistic means it has to be massive, that's what you're saying?
Yes, it behaves as a matter fluid in the early universe, just like dilute instead of redshift as well. And usually, in order to explain the relic abundance of dark matter, we need non-gravitational interactions beyond the standard model, okay? So, the WIMP paradigm, I don't know if you're all familiar or not, but this is like the most common...
Sorry for asking all these questions. Why do you need non-gravitational interactions? Why can't it just be interacting gravitationally?
It could be in some models, just like the relic abundance of dark matter being produced from gravitation. Usually just after inflation, we have the establishment of a dark matter relic abundance. This 27% of the cosmic energy today could be explained only with gravity. But usually, like the most, most models predict non-gravitational interactions.
Well, just because,
for example,
to make it a model. Otherwise, it's just so trivial that there's nothing to say.
Like, for example, primordial black holes could be produced only with gravity, but we cannot detect directly. So if we want a successful model and detectable model, usually is what we need, like supposed non-gravitational interactions. Now, the standard law of dark matter production in the early universe is similar to the production of baryonic matter. So we have a thermal equilibrium at first. So this is representing the expanding universe. And these purple dots are dark matter particles. And these orange are normal, the BAF particles, standard model BAF particles. And they interact, so the rate of production and annihilation are the same. So we don't have a change of number of these particles, of this species. But at some point, dark matter becomes too heavy to be produced from the BAF particles. So they just annihilate, okay? So the total number of dark matter goes down, and this is like following the equilibrium distribution until decoupling. So this is the freeze out. So it freezes out of equilibrium. And we have the relic abundance that we infer from the Planck satellite today. And typically, so the masses and coupling needs to provide this correct relic abundance in the end. And this is happening like typically for dark matter masses of from MeV to hundreds of TeV. There are also like theoretical limits about this because but I won't go into detail about it. We can ask if you want. And the couplings are at the weak scale. So they are weakly interacting, but not too weakly interacting. So, and this is good because this is within our technological capabilities to probe these new particles. So we can search for these particles, and this is what dominates the search for dark matter. Now, an alternative scenario is that dark matter is at first out of equilibrium. So some mechanism suppresses the number of dark matter, so it's not produced by inflaton, so on, or whatever. Like we can start with only visible particles, so only particles of the standard model BAF, and it starts producing dark matter. So there is some operator in the model that allows for the production of dark matter. And at some point, either because these particles that are producing decouple from the thermal BAF or so on, at some point this production rate becomes ineffective. So in this situation, the abundance, the co-moving abundance of dark matter levels off, and we can have, in the end, the same amount of relic abundance of dark matter. So this is another way of, but dark matter in this case never reaches thermal equilibrium. And this is because for this to be possible, the coupling strength needs to be very weak. So it's weaker than the weak scale. So usually we call this the feebly interacting massive particles, the FIMPs. So this is the freezing mechanism for production. So it's actually like the opposite situation of the freeze out, because dark matter is in the process of achieving equilibrium but never reaches equilibrium because of the interaction strengths are very suppressed. And that's what the particle physics model will give us. So basically, we have a lot of freedom for the dark matter mass in this case. It could be like from kV up to the Planck scale. And the interaction strengths, as I said, in order to avoid equilibrium, is very tiny. So it's very challenging to do phenomenology of dark matter if they are FIMPs, okay? Based on all of the evidence that as I said, dark matter needs to be gravitationally interacting particles, so it's the most simple explanation. And we have no idea about the mass scale of dark matter. So it could be from 10 to the minus 22 electron volts up to macroscopic scales, hundreds of solar masses. So we really don't know the mass scale of dark matter. And we have, of course, many candidates for dark matter particles that are viable, so that can explain this relic abundance of dark matter. And so we have the WIMPs, as I said, the FIMPs, but we also have sterile neutrinos involved with the neutrino mass generation. We have QCD axions, axion-like particles, and so on, and also primordial black holes. So when we have, sorry, yes.
Sorry, so I asked Rogeri, he said to ask you, 10 minus 32, how can it be non-relativistic?
So yes, it can behave as like oscillating field, but behaving as matter. So how'd say, it do not redshift. How'd say, it's a classical field. Like this axion, like, so this is the case of the QCD axion and axion-like particle.
So how is it different from a neutrino? I don't know what that means.
Sorry, different than neutrino?
Yeah, so neutrino is relativistic,
So neutrinos, so we do have, for example, if dark matter is a fermion, in order to produce because of the Pauli blocking, we cannot pack a lot of fermions indefinitely. Okay. So we have a limit. If dark matter is a fermion, or like a neutrino, if dark matter is a fermion, there is a limit, lower limit on the dark matter mass. So it cannot be much below the like 0.1 electron volts. But if it's a boson, we don't have any.
You're saying, so I'm not in the field, so I don't know this thing about coherent I've never heard before. So 10 to the minus 32 EV as a boson, can be non-relativistic. Can be non-relativistic, yes. Why? How? So it can be traveling slowly?
Yeah, non-relativistic is like the free streaming is not, how to say, it does not form like big structures that then go to small structures. I've not been didactic, sorry. It's like a classical field.
Okay.
But I never worked like with this particular candidate, so I don't know the details. But it can be non-relativistic. Like it can form structures because for what we say like cold dark matter is it forms like smaller structures that accumulates and form bigger structures. Okay. This hot dark matter form like big structures because it free streams a lot, and then the smaller structures would form later. But yeah, it is possible. I never worked with this kind of like QCD axion dark matter, but it's well motivated theoretically. Okay. And but in the way that we can search for these particles are different. It's like a wave-like particle, so like interference, we have to search for interference and so on, for classical fields.
Okay, okay, thanks.
So yes, we have like a vast, we have many possibilities to explain dark matter, many models.
So again, sorry, again, this is a little bit off stream, but what do you mean when you say non-relativistic, just to understand what that means?
I mean, it forms smaller structures first, and then the bigger structures.
Okay.
Behaving as, usually like it's behaved like a matter field.
Okay, thanks.
Not like radiation.
Great, thanks.
Mm-hmm. Yes, redshift as a H-3 as a matter component. Mm-hmm. Yes. So yes, if we solve for example, for the axion-like particles, if you solve the equations, the field equations, we can show that the redshift goes as H-3, so the matter component. Mm-hmm. It's like a misalignment and so on, but yeah. So most of the experiments searching for dark matter concentrate in this small region of the parameter space, because this is what is possible usually. So dark matter with GeV to TeV scale and couplings sizable, like just like comparable to the ordinary matter, can be searched for in like most like in telescopes, in underground detectors, and so on. So this is like most of the search for dark matter concentrates here, but it doesn't need to be, right? We have like a lot of freedom here. And as technology evolves, we can have like other searches. Now, the status of the WIMP dark matter, the search for WIMP dark matter, is quite, how to say, depressing, because we've been searching for dark matter, for WIMPs in particular, for 40 years, and we haven't found any WIMP. WIMPs are especially motivated because they appear in supersymmetric fields, theories, so, and people are being searching for supersymmetry, right? And but the status is that, at least like in the simplified Portal models or simplified models, the current experimental searches already ruled out the parameter space, and either rule out or will detect, maybe, we can be optimistic for detection, or it will rule out the remaining parameter space. So the current situation, here's a review on like the WIMP paradigm that we've done with collaborators. Basically, the multi-TeV WIMPs, and also next to minimal model, like with more than one mediators and so on, for example, 2 Higgs doublet model and U1, for example, they still can survive the strong limits, experimental limits. Okay, so the roadmap of this talk is to explore dark matter phenomenology beyond the WIMP paradigm. And so I will talk about new opportunities for sub-GeV dark matter, so light dark matter. Also scenarios with non-standard cosmology that we can, like, the models are safe, like it can be, how to say, like WIMPs can be not ruled out completely, so it opens the parameter space if we consider non-standard cosmology. And also theme phenomenology, so it's challenging, but it's possible in some cases. And then I will conclude with some perspective of future work that we could consider. So, starting with sub-GeV dark matter, as I said, we have like many candidates, and for example, in this range of from KV to GV is what we call light dark matter. We have a phenomenologically rich, how to say, situation, but underexplored parameter space, at least for the moment. So, and I will talk about our recent work that takes advantage of new opportunities with gamma ray telescopes, so MEV gamma ray telescopes. Now, this is a quite challenging, how to say, region of how to say, there is a sensitivity gap in the sensitivity of gamma ray telescopes in the MEV region. Like the X-ray, the X-ray telescopes are quite sensitive to new physics to dark matter, and also the GV, like above GV, the high energy gamma rays, we also have good constraints from Fermilab. Now in the middle, we don't have like much. it's difficult to constrain, and that's because it's more of technical difficulties. So we have low photomatter cross-section, and it's dominated by Compton scattering, and it's quite challenging to have Compton telescopes, like very effectively distinguishing a signal from background and so on. And we also have a high background. But the situation is changing. So we have a lot of new telescopes being planned and developed. And in particular, we have the COSY satellite. So it's a Compton telescope that is scheduled to launch next year. So next year we will have a new telescope that will be very good in particular for line searches. And I will tell why this is very interesting for dark matter models. So for the gamma ray lines. So we also have, I'm part of the COSY collaboration. So it's a very lively collaboration, it's a very nice. And hopefully if, in the best case scenario, it's launching next year, right? And we also have a lot of new MEV gamma ray telescopes being planned. For example, we have a GECO that is going to cover like a higher, so a wider range of energies, of gamma ray energies. And we also have a MIGO-X that would reach sensitivity close to the Fermi-Lat. So this would be, but this is like only for 2030. It's being developed and for the next decade. Okay, so I will talk about the model that we studied in order to predict very nice signals for the COSY satellite. Okay, so it's a very basic model of particle physics. Like it's quite a framework of new physics with different possible realizations. Basically, we have a fermionic dark matter interacting with the standard model through the exchange of a gauge boson associated with a new U1X symmetry. So we have this gauge boson Z prime connecting dark matter fermions and the standard model fermions. So it's a vector portal. And we, of course, we are assuming a new abelian symmetry, and that needs to be broken to the standard model symmetry. And we break this symmetry with a new scalar, so a complex scalar field, H prime, that gives mass to the Z prime. And in this case, I wanted to explore like a minimal scenario, so it also gives mass to dark matter and possibly to neutrinos. This is also possible realizations can, if we have like heavy neutrinos, bright neutrinos. So it's a very nice framework of new physics of dark matter model that also explain the stability of dark matter. Yes.
What's the difference between these and a regular dark Higgs model?
No, it is a Higgs portal. It has a Higgs portal like this. So this is a new scalar field that mixes with the Higgs boson, and it's possible as well.
Okay.
It's a Higgs portal, but also a Z prime. So you have both mediators. Mm-hmm. But yes, so since I want gamma ray lines, as I will show, this will be very interesting. Like, I will explain. Yes. You have a mixing between Z prime and Z? Yes. Yes. Depending on the charge assignments and so on, it's possible to have a mixing.
And in between the Higgs and this new scalar mediator
yes,
as well?
Yes.
Okay.
Yes. So, in this case, it's a complex field, but in this case, it will give mass to the Z prime. So we won't have a pseudoscalar in the end. It will be a Goldstone boson. Okay. Mm-hmm. Yeah.
This will change the couplings of the Z. So this will change the couplings of the Z boson, which is really well measured.
Yeah, if the Higgs, if the standard model Higgs is charged under this new symmetry, then it cannot have a mix. We don't have a mix between Z and Z prime. Because, yeah, the mass mixing will be 0. Because of, like, if we impose gauge invariance and so on. So it's, but in other U1X symmetries, it's possible with axial couplings and so on. So this is a minimal model, already with a lot of parameters, but it's a minimal model. So we have the gauge coupling and the scalar mixing angle. We have the masses of the new particles and the charges of all the particles in principle under this U1X. But this will be set by the choice of the symmetry that we consider, so the benchmark models. And we also have heavy fields, but it won't affect our phenomenology, so we won't consider this. So basically, we have this parameter space here. Now, gamma rays from dark matter are possible, of course, in many models, and this model as well. So basically, the flux, the differential flux of gamma rays coming from dark matter annihilation depends on the amount of dark matter in our line of sight, depends on the annihilation cross-section, right, the probability of producing gamma rays in the end, and in the spectra, the gamma ray spectra. So we have basically many different channels that are possible, and we need to consider all these possible channels. And the different channels will lead to different spectral features. So dark matter can annihilate into charged particles, for example, electron positrons, that radiate photons. And the spectra, it will be continuum. Okay, so it will be a continuum flux, like we would measure like the continuum flux of gamma rays in this case. Now, if dark matter annihilates into neutral particles that further decay into photons, we would have a box-shaped spectrum. And this is the case of this process here. So dark matter can produce H', because they are light in this case, in this model. Like if it's lighter than dark matter, it can produce H', that can decay into photons. And this will be a box-shaped spectrum. And finally, we can have monochromatic lines, gamma ray lines from dark matter when it annihilates into a photon-photon or a photon and another neutral particle. So it will be a monochromatic line at a gamma ray energy equal to the dark matter mass minus the term that depends on the mass of this possible other neutral particle that's produced. So this would be like, actually, if we measure a line where we do not expect any other astrophysical line, it's going to be a very, at least, a very good indication that it could come from dark matter. So it's a smoking gun signal.
Is this last diagram tree-level diagram or a loop-level diagram?
Always loop level.
It's loop-level.
Yes, because dark matter is neutral, and we always need some loop process here. In this model, as I will show in the next slide, we can have Z' or H' producing gamma-gamma, effectively. So this is, if we measure a gamma ray line and we can distinguish from background, this will be a very clean signal of dark matter, and it will give information about potentially the new physics that are needed for this process. So this is very exciting. And here I show you some, an example of the spectra, the gamma ray spectra, convolved with the energy resolution of the telescopes that we consider in this work. So COSY will have a very good, an excellent energy resolution, so of 1%. So it will measure the gamma rays very well, like the energy of the gamma rays very well. And this is very important for gamma ray lines, because if we have like a very bad energy resolution, we would see like a bump instead of a line. And a bump is easily distinguished, I would say, we cannot distinguish very well from other astrophysics process. Yes?
Of course, you're trying to sell us photons because you are in the collaboration, but you agree with me that the first diagram, for instance, the positron flux change will also show in AMS02, and I think it will show there before before you can see the photons.
Yes, but if dark matter is lighter than electron positron,
fine.
Then electrons, we cannot have this process. But COSY, all these gamma ray telescopes would also measure the continuum. It's continuum lines. But for example, the Fermi-LAT can constrain gamma ray lines, but they see the energy resolution is about 30%. So it sees like a bump. And a bump is easily any other thing. So this is the problem with indirect detection. We measure the flux, we measure the spectra, but we need to distinguish from astrophysics, from astrophysical processes. So yes, we can see here, Amigo X will have an okay energy resolutions, but sometimes it can distinguish a line, no? For example, in this case here. And here we have the box-shaped spectra. And this is like really distinguished from background. We don't expect boxes, gamma ray boxes from any known astrophysical process. But yeah, anyway. And it will give information about these other particles, these scalars that are being produced.
Can you say a few words about the background? What is the main background? The main astrophysical background?
The diffuse gamma rays from for example, for the center of the galaxy.
Point sources cannot...
Point sources as well, yes. But the lines, we do expect some emission lines from nuclear emissions, no? In the center of the galaxy in particular. But we hope that dark matter don't have a mass exactly at this particular, for example, the electron mass, the 511 kV line.
Yeah, the KV line is still there?
Yes.
It's 7 kV, something?
It's 7 kV?
What is the energy of the KV line? I forgot.
511 is the mass of the electron. It's
no,
electron positron annihilation.
Yeah, there's 511. Yeah.
Yes, it's quite... you mean the 3.5 kV
yes,
line?
the 3.5 kV. KV, right?
Yes, kV.
It's still there? No. Okay.
Yeah, because like the signal is not that like... The 511 is very clear that we have an electron positron annihilation, and the astrophysical sources are not enough. They explain some how to say, some aspects of the signal, some like the morphology, more or less, and so on, but it still can be dark matter. And dark matter is still a very strong candidate for that. In this case, dark matter produces electron positrons. So, how to generate strong gamma ray lines at the MeV scale in this simple model? It's not that simple, because, for example, we can have gamma ray lines for dark matter annihilation into H prime or pions and another photon, and also Z prime and photon. But the cross sections are weak, are not that strong. And this is a spoiler. The range that would be detectable by COSY would be 10 to the minus 34 centimeters cubed per second. So this is the annihilation cross section, right? And the cross sections are very weak, okay? And especially in the MeV scale here, that COSY would be able to detect the line. Now, we can have a gamma-gamma channel, in particular, for example, for the scalar portal. We have like H prime gamma-gamma, it's possible, but it's a negligible cross-section because the cross-section depends on the velocity of dark matter today, which is, since dark matter is non-relativistic, this will be suppressed, the cross-section will be suppressed, so we call this P-wave cross-section. And also, we have a Yukawa suppression because H prime chi-chi bar, will depend on the dark matter mass, the vertex will depend on the dark matter mass over the VEV, and we want a minimum model that explains dark matter mass with this scalar, and so it's suppressed. Okay, so and here we can see the cross section, for example, for U1 B minus L for this process gamma gamma, and we see the resonance for the mass of because of the exchange of the H prime and so on, but it's still weak. Only in the special case of a resonance region, when the mediator mass, so the H prime mass is twice the dark matter mass, the cross-section is enhanced and we can have detectable gamma rays. But this is a very special region of the parameter space.
So
now,
just a sec. So the mass of the Z prime is super light.
Yeah.
Aren't there, and also E plus E minus can generate the Z prime. You have a coupling with E plus E minus, right?
Yes.
So are there what are the bounds on this?
There are, yes. And this is a good thing that we can, it's a predictive model, and we can consider other constraints and to close this door, right?
It's super light.
It's light, yes. But it also, the constraints depend on how it interacts with standard model particles. And in this particular case, for example, that I would show here, that we have vector axial vector couplings, the phenomenology is different. So it's not necessarily, the constraints that comes from other, like standard Z primes do not necessarily apply to this case. But yes, we have a lot of constraints. And this is like good because it's testable framework. And if we have really a signal, like next year, with like of a gamma ray line, we can also search in other experiments to confirm, because only one signal is not enough to confirm the nature of the signal. Mm-hmm. So it is also possible to have a Z prime gamma-gamma effective interaction, but for that we need vector non-zero vector axial couplings. Okay, so the Z prime needs to be chiral. So the also, yeah, always loop left. Yeah, also loop left. But for example, this is the cross section for this for one axial U1. It depends on the masses of the other particles. So if they are light, it enhances the cross section and so on. Okay. So, because in this case we have a S-wave cross section, it doesn't depend on the velocity of dark matter today. Mm-hmm. So, because we need gamma ray lines, and because the gamma ray lines, strong gamma ray lines, needs axial vector coupling, in order to have the dark matter mass generation in this model, we need Yukawa term from gauge invariance, and we want a minimal scenario, so the dark matter achieves mass because of its interaction with this singlet scalar. And also the Z prime, so the masses are actually connected. We cannot have like a minimal Z prime model without in which the scalar field is much heavier and so on. We really need both mediators in this in order to have like a consistent model, right? And because we have non-zero axial couplings, we need new physics to restore the perturbative unitarity at high energies. And this is actually what we have in this model. So basically, dark matter annihilation to Z prime, the longitudinal mode of Z primes, would violate unitarity, so the cross-section would explode at high energies. And if we add a new state, a Higgs state, for example, this is the simplest possibility, we have this, let's say the perturbative unitarity is restored, so we don't violate anything. And the model is consistent. But because of this constraint, also the mass of this scalar needs to be also close to the Z prime and dark matter masses. So we have this constraint here.
So you want perturbative unitarity so that you can do a calculation, or for consistency of the theory?
Sorry?
You are asking for perturbative unitarity so you can do a computation, or because
yes.
you're worried about consistency?
Because to do
a
computations, yes, to be consistent with our approach of quantum field theory and so on. Mm-hmm. And yes, so usually what people consider is like a vector like dark matter without axial couplings, so this is not an issue usually. But because we want gamma ray lines, strong gamma ray lines, we need these axial couplings, and we need to worry about this kind of things. So we need both vector and scalar mediators. So these are the benchmark models that I don't know if I'm short on time, but these are the benchmark models that we consider. U1 B minus L is very commonly considered, and also axial U1. I won't give you too much detail about this. So I can start showing our main results. So here is the dark matter annihilation cross-section as a function of dark matter mass. And these colored regions here are already excluded by the gamma ray telescopes. So by COMPTEL integral, and also by the COSY balloon flight in 2016. So it's just like a balloon flight, but it's already, how to say, comparable to the speed limits, the integral speed limits. Here, like cross-sections above these magenta and pink lines are in tension with the CMB constraints, because dark matter would also produce photons and electron positrons close to the CMB release, so it would change the spectra of the CMB. So we also have this, and this is usually the strongest, the most stringent constraints for dark matter in the MeV scale. So usually people say that MeV dark matter is not viable because of the CMB constraints. But in some models, as this one, it's possible. And I will show why. So these curves here are the discovery reach of the future gamma ray telescopes. So in blue, we have the COSY sensitivity for line and in dashed, and for continuum in solid, and also the Amigo X. And we can see that it will probe dark matter parameter space beyond the CMB constraints. Okay? But we need to see what's the agreement with the Rayleigh abundance, right? Because this is really the viable dark matter parameter space. So, of course, that depends on the masses of the new particles. And here I'm showing the gauge coupling as a function of the Z prime mass. And the dark matter is the lightest of the particles, so it cannot produce electron positrons or H primes and so on. It only produces gamma ray lines in this case. And the freeze out is set by annihilation into Z primes, if dark matter is heavier than the Z prime, and neutrinos. And because of this, we have a viable Rayleigh density, Rayleigh abundance for cross-sections, annihilation cross-sections, much below the typical WIMP annihilation cross-section. That's 10 to the minus 26, for example, like we can see here in this other, sorry. Oh. Okay, so basically here, sorry. Usually the typical WIMP paradigm predicts cross-sections that high, so 10 to the minus 26. But in this model, it's possible to have lower thermal cross-sections because we annihilate to neutrinos. And okay, so
wait, this is still a WIMP model, not what you call the FIMP model. It's not freeze-in. It's
no, this is a light WIMP. This is a light WIMP because we are considering the freeze-out production.
okay. Thank you.
For the freezing, we also consider the freezing, but it's for gauge couplings much below this, the reach of these new telescopes.
Sorry, one other question. I'm sorry, one other question. On these plots, what line is gives the correct Rayleigh abundance?
Oh, I'm sorry. This black contour here. So in this case, we have, this is the resonance for the Z prime exchange. Because this is like a resonance in the cross-section. And because it's a resonance in the cross-section, we need very small gauge couplings to not overproduce dark matter. So that's why we have this feature here. And usually this is the region that evade all the constraints. This particular region of resonance. That depends on the mediator and dark matter masses. Mm-hmm. And so this black contour is the dark matter Rayleigh abundance, the correct Rayleigh abundance of dark matter. And these colored regions are the current constraints. And this dashed blue contour here will be the sensitivity of COSY for the line sensitivity of COSY. So we can see that COSY could see a gamma ray line for dark matter mass. Of course, this is dark matter mass is fixed, but for light Z primes and so on. Okay, and also like we can consider other mass hierarchies. So for example, if dark matter can produce H prime, then this process into, like the annihilation into H primes will dominate. The cross-section is huge, much like bigger than the gamma-gamma cross-section. And whenever this channel is available, we have like the viable region of the parameter space is already ruled out. So as you can see, it depends on the parameter space, right? The viable region that can evade the limits. So we need to have, in this work we did like a, I would say, we consider all the situations for the mass hierarchies. Okay.
And Maira, can I ask another question? Do you know in this WIMP like model, this freeze-out model, what the thermal distribution of the dark matter particles are? And in particular, if like neutrinos with 10 to the minus 3 MeV, keV probably are ruled out because they're too hot. So do we know what the temperature of these things are?
So these are like cold dark matter. These are standard cold dark matter, but a bit lighter than what is usually considered. So
I understand, but neutrinos.
It won't be,
So, how do they
the
compare?
freeze out will be non-relativistic, just as the usual freeze out. It's
So
not,
what would their temperature be compared to the cosmic microwave background, sir?
well, it would be that, so we don't.
Because the neutrino temperature, we know what it is, right? So that's why we were able to say it can't be less than
yes.
keV or something.
So it would be like the temperature of the cold dark matter. I don't know if I'm missing something. But it's like very cold, very non-relativistic today, and we don't have information about the distribution itself, but we can assume a Maxwell-Boltzmann and a distribution and so on.
Okay, thanks.
Mm-hmm. But yes, this is like standard cold dark matter, WIMP dark matter. Yes.
So these freeze out at temperatures below their masses?
Yes, it's non-relativistic freeze out as usual.
So that means the temperature, when the temperature is of order their mass, they're in equilibrium with that temperature, right?
Yeah.
And then when they freeze out their temperature, what happens to their temperature after that?
So it just like redshifts. Oh, sorry, just follows the how to say, as a matter component, like.
Okay, all right, thanks.
If nothing like a non-standard cosmology happens, no. But it's. Sorry if I'm not understanding.
Thanks.
Correctly.
No.
Yeah, but yes, this is like standard freeze out and non-relativistic freeze out. That happens like below the dark matter mass and so on.
Where do you, how do you do the calculation from the relic abundance? Do you have a
using micromegas in this case, because we have yes, because we have in this case just radiation era and so on. So we don't.
And do you know if micromegas get some special treatments for the resonance scenario case in there? Because I mean, it's kind of tricky to.
No, they do well. For the freezing is like a bit. Are you asking about the freezing?
No, just in the freeze out in the case of
no,
the resonance.
It's good.
Okay.
Yeah. At least I've been using for standard freeze out, but we can discuss if we find some, maybe for some particular models, but I didn't have. This is quite fast. The calculation with micromegas for this, it's quite straightforward. Mm-hmm. And so let me go on. So I'm a bit short on time. Like it's already 3. I don't know how.
You started late, so.
Huh?
You started late in the question.
Okay. So we can move into towards scenarios with non-standard cosmology. And in my talk tomorrow, I will give a lot of details about the dark matter production during reheating. So in an early matter domination, But here I just want to mention that the standard like freeze-out relic abundance and the freeze-in relic abundance will change if we have non-standard cosmology, if this production happens during an early matter domination. And this is because we have entropy production after the early matter domination, if it's long enough and so on. And in order to have the same relic abundance after this dilution, in the case of the WIMPs, they need to decouple much earlier. So they need to have smaller, like weaker interaction strengths. And then like we can have, well, I will show after. But yes, we need the freeze out to happen before the usual radiation as compared to the usual radiation era. In the case of the FIMPs, we need the FIMPs to interact much more with the standard model BAF in order to compensate this dilution. Okay, so these are opposite situations. In the WIMPs, we need smaller couplings. For the FIMPs, we need stronger couplings. And in the case of, for example, a very simple model, we developed this numerical code, EVO-EMD. So it's cosmic evolution with an early matter-dominated era. This is for freeze-out, freeze-in, and also leptogenesis with an early matter domination. So we solve the coupled Boltzmann fluid equations and so on with the possibility to have an early matter domination, just choosing the temperatures and so on. So we have like toy models implemented in this code. And for example, here we just have a quartic scalar interaction between dark matter and the Higgs field. And we see that if the couplings are strong enough, we have the freeze-out scenario. So with an early matter domination, the freeze-out, the correct relic abundance via freeze-out happens for smaller couplings. So usually, for example, if the constraints are ruling out like these stronger couplings, with an early matter domination, we can move the viable region down. And in the case of the freeze-in, we can bring the FIMP candidates to, we can become able to detect, for example, because we need higher couplings, higher interaction strengths if we have an early matter domination. Okay, so this is basically the case. We also considered MEV dark matter complementarity for the dark photon portal, and we found that we need quite a lot of entropy production in order for the parametric space to be viable. So these are the correct relic density, and we need so these colors here for longer and longer early matter domination and so on. But let me move on. We also considered sterile neutrino dark matter enabled by early matter domination. And for example, in this case, we have a 321 gauge extension of the standard model with active and sterile neutrinos in the same multiplet. And the lightest sterile neutrino is our dark matter candidate. However, if we just have that with a radiation era, so standard cosmology, dark matter is overproduced because the decoupling, the freeze-out happens at a temperature close to these gauge bosons, the mediators, which is much above the KV scale, of course. And dark matter is overproduced. So it's just like the neutrinos. Would be like a hot dark matter and so on. Now, since we have the heavier neutrinos, it's quite, how to say, nature to consider that these heavy neutrinos, which are long-lived because of this gauge boson mediator decays, so interactions, they dilute the overproduced dark matter, so the cold dark matter gets diluted, and also it injects a non-thermal dark matter component, because this decay also produces dark matter, and it do not thermalize. Okay, so we have a mixed warm and hot dark matter, right-handed neutrino dark matter. So here I'm just showing the solution of the coupled Boltzmann equations for radiation and the heavy neutrinos, in this case just one of the heavy neutrinos. And we can see also the entropy production and so on. But I will give more details about this tomorrow, and let's move on. And here we can see the tiny parameter space for this case. So basically this is the mass of the gauge boson, W prime, and the mass of this heavy neutrino. And the correct Willich abundance happens along these solid and dashed black curves here. So this is a constraint coming from the BBN, so this early matter domination needs to end before BBN and so on. And also we need non-relativistic decoupling of the code component, so this is also, this region here is ruled out. And we can see that we have a viable parameter space because of this early matter domination due to these heavy neutrinos. Okay, well, this is just to point out that non-standard cosmology and production mechanism beyond the freeze-out gives additional motivation to improve the limits of indirect detection, for example, because here, for example, is a 1 MeV dark matter, in this case very strongly constrained by the CMB because it can produce electron positrons, and this is quite constrained by the CMB. So we can see that the viable region is already ruled out by the CMB constraints, as is usually considered. But if we have early matter domination, the viable region of the parameter space goes down. So improving the constraints, we'll also find interesting parameter space from the theoretical point of view. And I don't know if I can, how much time do I have?
Yeah, go ahead.
Can I go? Okay. So, film phenomenology, as I said, is challenging, but it's possible, and I will just point out some scenarios where this is possible. So basically, most of the film phenomenology concentrate in collider signals, basically relying on the production of the films in the early universe. In this case, is due to the decay of a heavy field and a long-lived field. So it interacts very weakly with the standard model bath. So because we need that for the films to be a viable mechanism. We need a very small couplings, and this translates into long-lived particles that are decaying to films. And in the colliders, what happens is that, for example, standard model particles can produce these long-lived particles, but they only decay much farther than what is usually, what are like the detectors are usually set. So we have like, let's say, new proposals to put detectors much farther away and see and search for long-lived particles. So this basically dominates the film phenomenology, this kind of models. So we have SUSY models, we have scotogenic, doublet singlet, and so on. We have many models exploring this kind of this interplay between the film production and the collider signals. Okay, and we can also have light mediators that enhances the cross sections for the scattering of dark matter with quarks or electrons. So for light mediators, very light mediators, we can have detectable signals even for films, even for very small cross sections. And we also explored this possibility in this paper here. And in this case, we have a lot of signals, right? Different signals. Also, there is this paper here, like exploring this 3.5 keV line. Of course, it's a line. Now we know that it's a box spectra, but if the mass of the dark matter is quite degenerate with the scalar mass, this will be a line instead of a box. So the width of the box depends on the difference of mass between dark matter and this neutral field. But yeah, this is also possible. And in any particle physics model, as I said, if we have early matter domination, in particular long early matter domination, we need larger couplings between FIMPs and standard model particles, and this will be still out of equilibrium. So it's still, we have a FIMP candidate. And it becomes detectable because the couplings are stronger. So this is also possible. We also consider this possibility and we found that the Fermi-Lat and Hess could constrain some of the parameter space, but for very long early matter domination. Okay, so basically one interesting thing, like from the theoretical point of view, is that we can actually explain the smallness of the couplings with physics at very high scales. So for example, if we have intermediate scale, Z primes, and so on, we can have the suppressed cross-sections necessary for the freezing to happen. So it's very interesting, like from this point of view, to consider like more gut scale physics and the freezing production. But the problem with this is that it's difficult to do phenomenology to test these models. But we considered the same model. We considered monojet searches, and we found like regions of the parameter space in which we can constrain the parameter space of this model. So in this case, we have like a gluophilic portal. So suppose that we just have colored fermions interacting with the Z prime and the gluons. So we have this kind of freezing process here. So gluons produce dark matter in the early universe through the exchange of a very heavy Z prime. Well, not necessarily very heavy, but very heavy fermions. So that's why the cross-section is very suppressed. So this is our effective Lagrangian. It's very, how to say, suppressed, but it also depends on the momenta of these Z primes. So this is what makes this model testable, this momentum dependency of the couplings. So I won't give much detail, but we can have like approximations of, like analytical approximations of the relic abundance of dark matter, depending on all this, the parameter space. And we can see that in this model, since we have a very high energy dependence of the couplings, we have a high temperature dependency. And in this case, the freezing happens at the highest scales of, even before the reheating, the inflationary reheating scale, okay? So if we can see here, like the relic abundance contours are these dashed and black and solid black contours. So here's for 1 GeV of the temperature of reheating of 1 GeV, and here is 10 GeV, and we can see that the higher the relic abundance, we need higher Z primes to suppress, because the relic abundance depends a lot on the reheat scale. Okay, so we consider monojet searches allowed by this, enabled by these processes here. So we consider the Atlas collaboration constraints, but we can also have like new measurements and so on in run tree of LHC. And these are our main results in this case. So these are the correct relic abundance, depending on the reheating scale. And this pink region here is excluded by Atlas, by monojet searches. And we can see that it constrains some of our parameter space, providing the correct relic abundance of dark matter, especially for GV or lighter or sub-GV Z primes. Okay, and dark matter also likes dark matter. Okay. So let me go to the concluding remarks. Looking forward, we have new possibilities also with COSY, but regarding the detection of maybe primordial black hole evaporation. So because depending on the mass, the primordial black holes would produce MEV gamma rays, and COSY could detect this, for example, and we can have new results next year regarding this, regarding Hawking radiation, if we can search for this. And we can also see that we can start having complementarity between indirect detection and direct detection searches for light dark matter, for sub-GeV dark matter. So here I'm showing the cross-section of the scattering of dark matter of electrons as a function of dark matter mass. And for, like, if dark matter is above MEV in particular, we have the already like interesting constraints from direct detection. So we can combine with the limits from indirect detection that we will have in the near future. So, and finally, since COSY is launching hopefully next year, we can search for gamma ray lines. So it's very timely to consider more well-motivated models predicting gamma ray lines. Okay, so this is possibly many scenarios of particle physics models. For example, we can have axial-like particles as dark matter producing gamma rays, and we can consider more like complete models to really move forward, right, in this in constraining these models with this. We can also have dark matter producing gamma and neutrinos. So this is a nice connection between dark matter and neutrino masses generation and also leptogenesis, for example, if we detect this signal. So the parameter space will depend on also other open problems. And we can also, for example, consider two Higgs doublet models in which we have scalar, charge scalars, and this could enhance the gamma ray lines, for example, so for a process like this, for example. So it's very interesting to consider more from the theoretical side to build models that are well motivated and produce a detectable signal that we can detect next year. Okay, so that's all. As I said, like I hope to have convinced you that the nature of dark matter is something very pressing. Like we don't know the nature of dark matter, and it's one of the main open questions in fundamental science. And we have new opportunities to probe dark matter beyond the WIMP paradigm that is quite difficult right now, quite well constrained, but we have other possibilities to explore, other parameter space to explore. And in particular, we don't know the mass scale of dark matter, so a measurement like a gamma ray line could measure the mass, could point the mass scale of dark matter in principle. And we have a new telescope next year optimized for this kind of searches, so this is quite exciting. And also, it's interesting to consider like more realistic non-standard cosmological scenarios because they can enable new parameter space that we can search for. Okay, so that's all. Thank you.
Question? Scott, did you have any questions?
So you cited the Fermi-LAT. How the COSY compared? It's a naive question, but I don't know exactly.
So COSY, the energy range of COSY is from 200 keV up to 5 MeV.
Yes.
And the Fermi-LAT is like 10 MeV, for example. It loses sensitivity for lighter dark matter.
Okay.
So MeV scale dark matter is not quite well constrained by Fermi-LAT.
And the resolution, I believe, is also
the resolution
better.
is because it's a different kind of telescope. So Fermi-LAT is a pair telescope. So it measures the pair production from very energetic gamma rays that can produce the pairs. And the energy resolution is bad.
Okay.
It's like about 30.
Okay, thanks.
Mm-hmm.
So I had two questions. So you mentioned that the COSY telescope will see Hawking radiation?
Could see, yes.
When you say could see, Hawking radiation is unknown, is supposedly understood. So does it have sensitivity to see it or not?
It has sensitivity for some particular masses.
So it's dependent on the black hole spectrum? It's not dependent on the Hawking?
For this range of masses here.
But is there, I don't know, are there black holes at that range of masses? Or what? I'm curious what, why it's unknown if it will see it or not.
It wasn't detected yet, right? And we don't know the...
No, it hasn't been detected yet. But the
Yes,
question is,
so
if it will
but-
have sensitivity and it doesn't detect it, then there's a problem with general relativity and quantum
yeah.
mechanics. But
it won't be sensitive to like other mass ranges.
no,
It's
but
only
that's a different
particular-
question. I mean, the question of are there black holes at that masses? That's a different question. I thought.
Okay.
Do we know the answer to that, Ricardo? Or?
Nobody. I mean, you put a low. If you don't detect, you put an upper bound.
That's the only way we can detect those black holes is through Hawking radiation.
I think so.
Yeah, they're too small to do appreciable lensing. So
I see. Okay.
Yeah.
these are asteroid
they're-
masses.
Yes, they are very...
I see. Okay. Thanks.
Mhm.
Sorry. Yeah. Yes. Yeah. Yeah. That's unfortunate. So the other question is more philosophical, but suppose what do you think is the probability that we will eventually have direct detection of dark matter?
Direct detection?
Yeah, or some detection besides just indirect.
Yeah, we've been searching for 40 years.
Yeah, but so you're
We
working
don't-
in the field. I'm just asking. People ask me
Yes.
all this time about string theory, about what's the probability. So I'm asking you, for dark matter. I mean, you're devoting your career to it. So
we
the
have days
question-
and days.
Sorry.
we
No.
have to keep the hope to
No.
detect
I'm
some
asking if you
signal.
had to bet, what
But it's
would be the?
I think any new opportunity, any new detector.
No, that's not what I'm
it's-
asking. I'm asking, if you had to bet, you know, what do you think is the chance that within 20 years there'll be some detection of? Is it 50%? Is it 5%? Is it 95%?
I'm super agnostic. I don't know. When there is
0%.
Yes, I mean, but even the neutrino. So for the direct detection search strategy, we expect to detect dark matter scattering, but for very low cross sections, it would scatter just as neutrinos. So the background would be irreducible. However, there are opportunities to, for example, see the direction of this of the source of
I
the.
suppose it doesn't interact except gravitationally.
Oh yes, it's possible.
It's possible, it might even be probable. Is there a reason why it should?
I don't know, because we don't have. I mean, in principle, any model is possible.
No, I'm
Or-
not asking if
or
it's possible. I'm
probable.
asking if it's likely or unlikely.
It's difficult to. I don't know if we
Okay.
can answer that.
Okay.
But there are the well-motivated models. That's the point. Like,
But the community thinks that it's unlikely that it will be just gravitationally, or does the community not
I
care?
mean, but
or?
we need to explain the neutrino masses. So we necessarily need new physics and beyond gravity to explain the neutrino masses.
Okay, and you
So
think
this
that might
is-
be related to dark matter?
It can be. So
Okay.
if we relate dark matter to neutrino mass generation, it's a well-motivated approach, because we already know that we need new physics.
Two
for
problems,
neutrinos.
maybe you'd like to. Okay, anyways, I think it's a philosophical question.
Can I rephrase the question? So is the WIMP paradigm completely dead,
No.
or is still the corner?
No, it's possible.
It's still
Yeah.
possible.
Like we have parameter space in many models that can produce a signal. No masses and couplings that can produce some signal in direct detection experiments. Sometimes it's in this particular region of the resonance, so it's quite, how to say, fine-tuning. But it's possible. It's not dead. It's not dead. Especially for heavier multi-TeV WIMPs. It's still possible.
So from few hundred GeV up, it's
Yeah, even for the GeV-TeV range, it's possible to have, because we still have parameter space. Of course, it's not ideal situation. Like we have many models, and we don't see a signal yet. And okay, we can change something in cosmology, and But I mean, I think it's the best we can do for dark matter because we know we have a lot of evidence, we know it exists, and we need to explain. It's frustrating, but it is what it is.
Okay. Any other questions? Okay, so thanks. Let's thank Maira again.
Thank you.